All right, everyone, welcome to the set theory seminar. Today we have Yuxin Zhou from the University of Florida. He will be speaking on coloring isosceles triangles countably in R2, but not in R3. He will be using a mixed media here. So he will be using his slides and his board as well. And it seems what we've determined after some playing around is that if you want to see the board, you just click on his picture where he's writing on the board and you say pin, and that will show you the board, and then you can, and then it will have the option to go back to the shared media. So you can toggle between the two. We haven't done this before, so I'm curious to see how it will work. Go right ahead, Yuxin.
Yes, thanks for this wonderful opportunity for me to present my thesis. And I apologize for the inconvenience of using this technique that I wanted everybody to be doing. So let me start by showing you the outline. I have introduction and then introduce a balanced forcing and define my pole set P to force, and then the main theorem and the main proof of the theorem. And depends on the time, I will survey some details hidden in the main proof. So as a background, the partition or coloring problems under ZFC, a theorem says that there is a partition of Rn into countably many sets, no one of which contains the vertices of an isosceles triangle. It was conjectured by Erdős very early for all n, and Erdős and Kakutani proved n equal to 1 case. That's just gonna be the 3 points on the real line with equal distances. And much later, in 1972, n equal to 2 case was proved by Davis, and then for all the n, proved by CUNY. And later in 96, given the axiom of choice only without continuum hypothesis, it's proved for any n. Also, there are some other results. So partition of Rn into countably many sets, and none of which contains the vertices of an equilateral triangle by any n case by Schmurl in 93. And Erdős and Komias in 1990 showed that there is a partition of the plane into countably many sets, none of which contains the vertices of an right-angled triangle, is equivalent to the continuum hypothesis. And it's in fact also it's true for higher dimensions too. Later, Schmurl provided a complete classification for the chromatic number of any algebraic or hypergraph graph. Gamma on Euclidean space satisfies a trichotomy. ZFC proves either the chromatic number is countable or the chromatic number is uncountable, or there is a natural number m such that the chromatic number is countable if and only if the continuum is less than or equal to enough M. And in addition, we even can have a computer program that can output the number M if you input the hypergraphs equation. You see algebraic hypergraphs. So we wonder that what without axiom of choice, can we do classification like that? So it turns out to be much more difficult, and we often even realize or expect the case that the countable chromatic number of one hypergraph doesn't imply another, except the obvious ones. For example, if you can color one kind of hypergraph in higher dimension, and then of course you can color the lower dimension version on Euclidean spaces. So this is the main theorem for today. It is consistent related to inaccessible cardinal, such that if plus the dependent choices holds, and gamma 2 has countable chromatic numbers, while gamma 3 has uncountable chromatic number. I didn't introduce them, so my gamma 2 is the isosceles triangles on R2, and R3 is isosceles triangle hypergraph on R3. Two difficulties. So we want to invent a suitable forcing poset to add a countable total coloring, as I call it, the positive part of the work, and then the negative part, which is to refine the poset to be fine enough so that it doesn't add countable coloring for another hypergraph. So if we achieve those, then we can have such independence result. The technique is balanced forcing over Solovay model, the symmetric Solovay model. So the background for Solovay model in 1970s from a model V of Leaf, from a model V of Leaf's with an inaccessible cardinal, one can build a model of Leaf DC, and all sets of reals are the big measurable and have bare and perfect set properties. And immediately the full axiom of choice will fail. Let K be an inaccessible cardinal, and the poset is gonna be the collapse omega less than kappa. And we take a generic filter G over ground model V. The symmetric Solovay model W is HOD, meaning hereditarily definable. The model of all hereditarily ordinarily definable sets with parameters in the ground model V and the bare space or reals, computed in VG. That's our Solovay model. And then about the balanced forcing. So just a short definition here, but in fact, it takes some work to rigorously set up all the definitions for this balanced and what it means to have a virtual condition. So let P be an analytic forcing, and P is balanced if every condition let P in the poset P, there is a balanced virtual condition below P. Shortly speaking, the balanced condition most likely is not a condition, but it will be a condition if you apply the collapse forcing, shortly speaking. Given some algebraic hypergraph or graphs, gamma 0, gamma 1, we want to find a cofinally balanced R analytic poset, and to force using that over the model W to get WG. And that will be the witness model, so that we have countable chromatic number for gamma 0 and not for gamma 1. Actually, in my case, I call them gamma 2 and gamma 3 for today's theorem. The poset needs to satisfy. So each condition will be the countable approximation of countable colorings of the first gamma, or the zeroth gamma, partial colorings, and ordered by strengthened reverse extension. And P with the ordering needs to be transitive and sigma closed. And P is analytic. So by the way, as introduced in Lars and Zapletov's book, Geometric Set Theory, it's all called isosceles rather than analytic. But we realize that it's hard and extra work to make it isosceles, which means to make all the definition borrow. And we don't have to do that. So we just stick to analytic, and it will be fine. And then for every letter P, the support of P, subset of the reals, is a countable real closed subfield of real. And then the item before the last item just says we can, for any letter P, for any point, probably outside of the domain of P, we can extend the P to some Q, that the domain of Q will include the point. So we can extend the coloring to an arbitrary point, arbitrary new point. And P is cofinally balanced. Just being balanced is not always possible, but being cofinally balanced will be sufficient, which means cofinally you can force a model throughout the extensions such that the P is balanced. It will show up later. So a theorem by Lars and Zapletov in all cofinally balanced extensions of symmetric Solovay model W, every well-ordered sequence of elements of W belongs to W. So it doesn't add new such sequence. As a consequence of it, our methodology has a limitation, a theorem by Zapletov, saying that there's no cofinally balanced isosceles or analytic forcing which adds a total countable coloring for the right angle triangle hypergraphs. Therefore, we cannot obtain a model such that we have a countable chromatic number for the right angle triangle hypergraphs using this methodology. All that takes some proof, but let me not mention today. Just slides to have the basics for the real closed field. The key points that we will make use of is it has quantified elimination, and the real closed subfield of R will be an elementary submodel, and of course, real closure property, which is convenient, useful for us later. So I was trying to go relatively fast so that I can get to the more important stuff. Any question before I move on to define my pose? We can always come back to the details that I kind of either skipped or too fast. So gamma 2 is hypergraph of isosceles triangle on R2, and gamma 3 is the one on R3. The countable coloring for gamma 2 is a function from R2 to natural numbers or countable set, such that no vertices of any isosceles triangle will get the same color. So let's start to define the pose set. Fix an ideal I on omega contains all finite sets, and it's not generated by countably many sets, so that it's pretty large. The particular choice for the I doesn't matter for us. So our pose set P is all conditions little p such that the support of P again is a countable real closed subfield of R, and the domain of that is just the square of the support subset of R squared, and P will represent coloring on domain of P, gamma 2 coloring, countable. And the third item is I call a symmetrical colors requirement. It says for every line L visible from domain of P. If you have 2 points in the domain, then the line passing through the 2 points is visible. So for every line L, the S is in I, where S just means S is a set of colors of pair of points that have the same color and they are symmetrical with respect to L. So I throw all that colors, well, I call that S, set of those colors, and it's in I, which in a sense means that I want the set of colors to be small. And then even more importantly, in a sense, is the ordering of the posing. So, and it takes much more time too. P1 is stronger than P0 if the domain is bigger and P1 agrees with P0 on P0's domain. And so 3 last ones are pretty important. Maintaining symmetrical colors requirement says that the set S doesn't grow. Because that's for our sigma closure. Probably, I can just quickly draw something here. Because when you take a countable infinite decreasing chain of P's, then you don't want the set S just add up to occupy all omega or most of omega. So that would be too many colors. So that's for sigma closure, and the avoid center requirement is for whenever we have a circle, we want to, the new point on the circle wants to have different color as a center. And this is a way to possibly, well, it actually overkills. It avoids all possible, well, I mean, when we extend, it avoids the possible monochromatic isosceles triangle on the circle with the center of the circle. Also, by the way, for the lines, so essentially we are dealing with lines and circles. So whenever you're given 2 points there and there, every point on the line will form, with those 2 points will form an isosceles triangle. So that's the place to attack the coloring question. And last one, it seems mysterious for now. I may tell you a little more later. It says for every finite set A subset of the bigger one, the support of the bigger condition, the P1 image of the set of algebraic points over the smaller support union the finite set A, the P1 image of that is small in I. So the main theorem, or the theorem that will immediately give the main theorem, is let kappa be an accessible cardinal, and there is a model of ZF plus DC in which gamma 2 has countable chromatic numbers, while every non-mingle set A subset of R3, it contains all vertices of an isosceles triangle. And this will do the job because we still have bare categories here because of dependent choices. And so whenever we are trying to partition R3 into countably many pieces, one of them will be non-mingle. And we will find the vertices of isosceles triangle there. Therefore, it's gonna be, all of them will be in the same piece, or equivalently, they will have the same color whenever we trying to do a countable coloring. So this here is the main proof, the mechanical part of the proof, and details will be hidden many places. But let me present this, otherwise there will be no proof. Although it's more fun to talk about the details, and that will depend on how much time I will have left. So let's see how it goes. Let W be the symmetric Solovay model derived from kappa, and the model we need is just P extension of W. Call that WG, and that's what we need, just to repeat what we had. Working W, suppose we have P is a condition and tau is a P name for a non-linear subset of R3. We want to find a gamma 3 hyperedge in it, and strengthening of the condition P and force it to be a subset of tau, and that will do the job. Now here is a property of the Solovay, symmetric Solovay model. The P as well as the name tau will be definable from the ground model parameters and the additional parameter, I should say, omega to the omega, but they actually are interchangeable. And let Vk be an intermediate model obtained by forcing of cardinality smaller than kappa, such that our parameters are found there. And continuum hypothesis holds. So let me just state right here in the parentheses that my poset P will be balanced in Vk if CH holds. So P is not balanced everywhere, but whenever we force CH, we are balanced. Working the intermediate model Vk. So let P bar be a balanced virtual condition. So again, it's not a condition yet, but it will be once we apply the collapse forcing. Consider the Cohen poset P R3 for the R3 of non-empty option subsets ordered by reverse inclusion. And it's gonna add a generic point for R3. So here's a main claim. There must be a condition O in that Cohen poset and the poset Q of cardinality smaller than kappa, and P R3 times Q name sigma for condition poset P stronger than P bar, such as this happen that I'm gonna write and draw on the blackboard through my camera. So let me just go ahead and do that now. So please everybody switch to the camera view. So I have these forcings here, and I will draw a picture with it. So basically, we want to make this happen. So the generic point will be in the non-mingle set. So we have we start from VK actually as a ground model, and everything is inside. Here. Solve a model W, and to get solve a model, we have this collapse forcing to get to this bigger model, and then we do the HOD to shrink down to the W. So now everything's in W. And first we have the O. O is gonna extend the VK. So by O, we have a generic point. And then the Q is for the name of the condition of P. So Q, so we have that. So in Q, we have the sigma, and then collapse, so that the virtual condition will be a condition when we have the collapse. And the beauty of the Soloway model is that if we apply the same collapse, in fact, we go from the intermediate model to the big model, and then HOD will be W. And finally, we have the P forcing by our poset. So that's gonna be the P forcing over so W, and that model will be so that's gonna achieve this whole formula. And let me go back to read my slides. Otherwise, so I claim this must happen. Also, along the way, I use the properties of Soloway model so that we can have all that. So otherwise, if this doesn't happen in model W, the virtual condition P bar would force tau to be disjoint from the co-mingle set of points in R3, which are coherent generic over the model VK. That contradicts with our initial assumption that the tau will be a non-mingle. So far we see how to shoot one point in R3. Then we want to shoot three points, and they form isosceles. They form an isosceles triangle inside the tau. So let me go back to my slides. So I'm on my slides. So now, instead, consider the Cohen forcing poset P of gamma 3 bar. I didn't define, but the gamma 3 bar is a hypergraph, but I put an order on it. The middle, the middle coordinate will be the pivot point of the isosceles triangle. And it turns out,
Yuxin, sorry,
yeah.
should I switch the view back to the slides, or do you still want the view on the board?
Yes, please. Back to the
For the
slides.
recording. Switch to the slides?
Yes, slides.
Okay, it switched.
Okay. Although I somehow don't see my, okay, that's, gamma bar 3 turns out to be a Polish space. I think I have slides later, more details for that, because it's a G delta subset of R to the 3 to the 3. And we do the Cohen forcing with that space, gamma bar 3. And then we have a generic triple E for that. And we want that to be meet O to the 3. So everything will be in O. Observe that each vertex X in E, X is PR3 generic, and each pair of vertices in E is mutually generic. By the openness of some projection maps that I will skip for now, but I have slides later, and depending on the time. And those are non-trivial works. So now we have HX for every X in E. So 3 of them to be filtered mutually generic over the model VKE. So we have the VKE HX. So 3 looks like 3 here. I should be drawing pretty soon. 2 observations that, so those 3 models will form a delta system with root, the ground model. And there's no isosceles triangle in R2 with each vertex in each of the model. I probably should say other than the intersection, other than the ground model. I will, let me finish this slide, and then I will draw. So given that, what I stated, then I claim that we can find a common lower bound whenever X is in the generic edge E and PX is a condition in each of the model, and stronger than P bar, we can have a low bound. And to finish this proof, for each X in E, we have PX to be the sigma over X, so which is a condition in each of the 3 models. And by the forcing formula we just had, so instead of 1, we use that 3 times. So they all do the same thing. And then we can have lower bound Q for Px, X in E, three of them. So we have produced a gamma 3 edge E and the condition Q stronger than P, and forces all the vertices in E to be in tau as we wanted. So let me go to this camera view. So please click the me with the in the camera. So instead of one, we have three of them. Looks like that. I instead of drawing in W, I draw that. So it'll be there like that. One important claim is that I didn't add isosceles triangle in R2 like that. Then, so that's actually, so whenever we have a condition, say X, those are the conditions, we can find a lower bound Q. Q will be in our coloring pose at P. And that will do our job. The Q will force all the vertices to be in the non-mingle tau. And that will be the end of the proof, but I have many details. I wonder how much time do I have left? And anybody's questions so far? There are many skips, in fact.
You can have about half an hour more at least, Yuxin. So that's
okay.
But do you want me to switch the view now?
If nobody has any question, I will switch to the slides. So okay, so let's switch to the slides. I mean, anybody is free to switch anytime. I kind of hesitate to go to the board more freely because everybody have to switch with me. There's one detail that so we want P to be balanced with continuum hypothesis. The key is to show that P has amalgamation property. Which means that if you have oops. Let me just probably just draw that on the screen. So you have P1, P2 stronger than P0 with some prerequisites. Then you can find the P3 stronger than all of them exist. So let me mention some difficult case. So whenever you have P1, P2 with their domain like that, you want to extend to include an arbitrary point outside. The difficulty is that there may be many isosceles triangles like that, monochromatic. Well, those pair of points on the base is already monochromatic. It could be a different color. And there could be countably infinite many isosceles triangle like that, so that you will run out the color when you color this vertex if you try to extend. And how we avoid that is to it takes a long time actually, but I claim that whenever this happens, all those vertex, so maybe so let me say like that. The intersection, it's a real closed, countable real closed field. Union the 2 points in my green bubble on the right. And every other point on the right is algebraic over my 2 green bubbles. It takes some algebra and model theory to do this, and also it means that I have to set up my definition of my poset right for this. And remember that, or it's pretty hard to remember. I had my definition here, the item 8. It requires precisely that all those points don't have many colors. They in fact have small number of colors, so they all in I, and we are good. We have plenty of colors left when we color the vertex outside. It's still pretty on the surface of it. So that's one. Any question about this? That's one detail there. Of course, there are other configurations and stuff. I can't erase all at once. So, by the way, this is one of the detail for my positive part to add a coloring. So next, there are a bunch of things for my negative part, which means that we do on the board that there's no coloring for the one in R3. And I mentioned that it needs to check several open maps so that we can do a hyper edge forcing that I will tell you. So that's my gamma 3, but put a bar on that. That's subset of R3 to the 3 ordered hypergraph, and with the middle coordinate to be the pivot point. It's in fact a G delta subset. It's in fact it's an algebraic hypergraph, so it's closed, but we want to exclude the diagonals, so because the vertices need to be distinct. So that's G delta and the Polish space. Then we can do cohen forcing with it, and that's gonna add ordered hyperedge for the hypergraph. By the way, right now I'm working at instead of do the cohen forcing, I'm thinking about whether I can do random forcing instead of this, and it turns out to be more complicated. This cohen forcing, with that to work, it's already takes some work. So proposition saying that the G subset of R and M to be G delta, and assume that's invariant under similarity of Rn. It means that you have a hyperedge, and then you apply them by a similarity of R, which means you can. So every distance is stretched by a same scalar. Then, so maybe you can also rotate too. It's still a sausage triangle. So that's our hypergraph satisfies this property, and then projection of G into. So projection of G into any two coordinates is an open map to the Rn squared takes some work, but there are a few more others. So our gamma 3 bar satisfies that, and so we have the open map to any two coordinates, open map to the target space. That a quick corollary is that when we force the hyperedge, we will have every pair of those three vertices is mutually generic for the product forcing of Cohen forcing for the R3. That's what we used in the main proof, and there is more. Complicated ones. Yes, so this is proof. The claim was proof that there's no isosceles triangle in R2 with each vertex in those each of those three models. For this claim, we need more complicated open maps and hyperedge forcings. So I have a definition like that, but you don't have to read. So let me just, so I'm defining duplication of a hypergraph. It just means I will just draw a picture and you will see the meaning rather than reading. So the hyperedge was like that. So say my zeros vertex is there. So if I duplicate by 2, there will be just one more like that, and they form isosceles triangle like that with 2 other vertices, and so on. You can duplicate by k, so on. And all of that points form an hyperedge for the duplicated hypergraph. So that's what it means. And then I want a proposition saying that the projection of, so I duplicate, oops. I just quit myself. Sorry about that. Any question so far? Let me join and pass code again. Any question, just let me know.
Are you able to get in?
Yes, I'm getting now.
Okay, good. I see you. Mm-hmm.
Yeah, I just randomly killed all programs.
All right, you're in.
Okay. Share. Back to here. So duplication, so I duplication 4 times. So gamma 4, 3 bar. From the my zeros vertex. And I say my G is stable against 4 vertices. So if you ask what's a core geometric or combinatorics or algebraic fact to distinguish those 2 hypergraphs, it's this one. This is a key. Stable against 4 points. I didn't write down the definition here. It's actually kind of hard to read, but it basically says so a hyperedge looks like that. So I'm duplicating my I'm duplicating my this vertex, and I can duplicate 4 of them at most. So there are 4 of them. They all form a all form isosceles triangle with 2 other vertices. Whenever I have 2 vectors applied to the base points, 2 other points, there exists a similarity phi of the whole space R3, such that it moves every point, in particular, those 4 points. And they all stay in this hyperedge, which means they are still isosceles triangles. In addition, so let me actually label this U0, U1. The map U0, U1, actually it's a functional maps to phi is continuous. That's a key difficulty. Without continuity, more or less, well, of course, you can achieve that, but the continuity is the key. The pair of vectors maps to the corresponding similarity is continuous. The topology on the space of similarity is pointwise convergence topology, and that's continuous. And that's a key or difficulty. How can we raise? And the max number is 4. For our case, like the one key is that 4 vertex decides a sphere. So for 4 vertex decides it's not a good sphere. And 5 is too many. So for roughly the idea behind this is 4. So it sounds like that. So for isosceles triangle in R3, we are allowed to duplicate by 4 here and by 4 here and 3 here, but we don't have to use that. While, so this is in R3, while the one in R2, the numbers are 3, 3, 2. Isosceles triangle. So that's the geometrical combinatorics distinguish between those 2 hypergraphs. And somehow so through those propositions and corollaries and so on, and we can put them together to make this proof work. So let me just read what's the consequence. The projection to the last 3 coordinates is an open map, and the projection to any 2 coordinates is an open map. Let me emphasize one thing here. This is the open map to the space of gamma 3 bar. The target space is important. It has to be open map to that ordered hypergraph space. And the key idea is stable against 4 vertices. So that's something to pay attention to. Corollary is what happens if we do the forcing to force that hyperedge, duplicated hyperedge. So e to the 4th to be generic over that P of gamma 4, 3 bar, and then the first 4 points are mutually generic. Any 2 points are mutually generic. And the last 3 points and a little more is generic over V for the poset P gamma 3 bar. And then let me erase before I turn the page. Oh, that's the end actually. So that will maybe come back to here. That will do this claim and this claim with many things else will make our main proof work. And last page is my my thesis paper in preparation on my website and my email. If you want to look into the details. So let me stop here, unless people have specific detailed questions about what happened. Thanks everybody's attention.
Thank you. That was very nice. I was surprised. I wasn't even aware of these results of connecting the chromatic numbers with CH, and it's interesting that it needs choice. So super, super interesting. Questions?
Although the balanced forcing can do many other things there.
Yeah. I mean,
not just the chromatic numbers, it can distinguish. So the basically, I should have mentioned, is that it's for distinguish, let's show the independence between two sentences. One is true and one is false in some model that we can construct. And that's approach. And let me mention that the main proof basically looks the same as this, just mechanics going through this Soloway model inside and do that. But the details is for today's, as I mentioned, what just happened for the duplication and so on. That would be different every time.
all right. Does anyone have questions for Yuxin? Going once, going twice. Okay, so I will stop the recording then. Let me see, how do I, oh, here we go, perfect.